But the usual thing is that when I'm at a conference, I know, say, 70 to 80% of people. Here it's the other way around, because, and this kind of explains a little bit of convoluted title. My original goal was to see whether tensor networks, which have been applied a lot to model Hamiltonians, can actually be made useful for real materials. And this somehow dragged me into the world of flat bands in the form of lithium vanadate. And as I saw on the sort of like speakers list that there would be Professor Takagi talking about experiments in theory of lithium vanadate, and I guess Ricardo, will also talk about that material afterwards. I shortened a little bit the part on the material and stuff and explain more about what we aim to do here with tensor networks, because what I would like to show is that maybe this is one way forward to address some materials where it's really hard because of extremely small energy scales that have to be resolved, for example, when they're very narrow peaks. So, of course, we all know here in this room about DMFT as one of the methods to address the problem of correlations in transition metal oxides and rare earths. And you all know that basically the idea is you replace the interacting model by an interacting impurity, which is embedded in an effective bath, which is non-interacting, where the impurity dynamically exchanges electrons with the bath. And there's a self-consistency because, of course, the one site or the group of orbitals you have chosen should not be special compared to the rest of the material. So there must be a self-consistency condition. And here it's a dynamical condition on a Green's function and a self-energy, respectively. This method is known to be exact in the limit of infinite coordination number, and it goes back to the work of Antoine and Gabi Kotlia in '92, has been used by numerous groups, well, a multitude of groups. And of course, one of the big ideas over the years has been to make it more realistic. Of course, it started out with, say, the single band Hubbard model. And so people have moved to multiple bands, to cluster models, to get more information about K-space resolution, to combine it with DFT, to have realistic band structures involved, and so on and so forth. This is not the place to talk about that here, but what has always been a key problem in the development of this method, and this is where sort of like my or our work comes in, is that at some point you have to calculate a time-dependent Green's function for this impurity, be it one orbital or many orbitals, in time, where the time can be real or imaginary. That depends on the method. And this is what you have to do there, is sort of like colloquially called the impurity solver. And in many ways, this has been one of the key areas of progress in the method. So everything started out with methods like the Hirsch-Phi Monte Carlo. This has been completely replaced by continuous time quantum Monte Carlo, which I think is now the go-to method at the moment. There's also a means of doing it by exact diagonalization or by using the numerical renormalization group. So when you do that, the question, of course, has always been what could be the role of tensor networks. Tensor networks have developed to be an extremely powerful numerical method for low-dimensional model systems, and this is basically what brought people. And I look at, at Olivier, who we discussed that first 20 years ago, and there you see about the difficulties of doing all that, that if one looks at how NRG is one of the go-to methods for dealing with impurities, how this deals with an impurity embedded in a band. Of course, it need not be. What's going on here? Anyways, you see, somehow the pointer is not working, but anyways, sorry? Anyways, I have my hands, otherwise there's a stick here. I think we will go back to analog solid state technique. So NRG maps this problem to a one-dimensional chain where the impurity sits at one end and there are bath sites. There's, of course, many details involved in that. But if one sees a picture like that, one would say, well, the so-called matrix product states, this is a tensor network in one dimension, is incredibly powerful there. So why doesn't one use that as... Sorry? This one works. Thank you very much. Does it also? Okay.
Go ahead.
Yeah. So thank you very much. That's very kind. So it has. No. This we get that. Okay. So one just has to tell it, ignore it. Okay. So let me get rid of the solid state technique and see whether more advanced electronics does it.
There's a mirrored projector, so it will bounce back into the audience.
Okay, good. So I'm not allowed to use that, so we go back to solid state techniques. Okay, so there is no sign problem, which sometimes might hinder Monte Carlo. You can do calculation on the real frequency axis because one has time evolution techniques, so that is something which QMC and exact normalization have sort of trouble with, and there's no exponential growth of resources which is hindering exact normalization and NRG. So this is the so it works this way. Sorry. So this has been the sales pitch, why one should try to use tensor networks since around 2004. And the question is, of course, why is not everyone doing this these days? And the reason for that is that the time evolution in tensor networks is hindered by a very deep quantum phenomenon, by the growth of entanglement. And so to see why and where the progress in the method is, let me briefly walk you through a one-slide introduction of tensor networks, and in particular, let's take these simple matrix product states. You have the exponentially many coefficients in an expansion of a state in a Hilbert space, and you replace these coefficients by a product of matrices which have some finite dimension. You can draw a picture of these matrices, so they all have an index, which is the physical index of, say, spin up, spin down, or empty, spin up, spin down, or double occupancy in a Hubbard model. This is sort of like the row and column of the matrix, and that's the physical leg sticking out. You contract those guys, and this gives you these coefficients, of course, only in some approximation, because there is not exponentially many coefficients available there. And it's, of course, the entire point about it. What you typically do for that is apply it to model Hamiltonians, has been first used by Steve White in '92. There's a bunch of reviews which I advertise here. And you can extend this method to more complicated tensor networks, and that's the one which we will also be looking at here, like tree-like structures where you have tensors which have three legs sticking out and give you branches. This has been also very important in successful. But the point is, how good can this actually be? How good can such an approximation actually work? And I think everyone knows how entanglement is defined. And if you look at it in terms of these matrix product states, say this is the subsystem A and the B, blue and red, how are they entangled? So what you find out is that because you are multiplying matrices together, whatever is happening here or there is, if the matrix has, say, dimension d times d, there's d rows speaking to d columns, just what happens if you multiply matrices together. So, in fact, any quantum state which is represented in that form is then a superposition of d pairs of states, not more, not less. And from working out reduced density matrices, one finds the key statement, namely that the amount of entanglement that you of a quantum state that such a tensor network state like this one can encode is limited by the logarithm of the dimension of the matrix. So this is not necessarily much, and of course we know classical efficiency is much less than quantum efficiency in terms of computation. And what one knows, however, that why we get away with this in practical simulations is that for many states, in particular ground states, low-lying states, it is not as bad as it looks, because normally we are used to entropy, because entanglement has the form of an entropy here, grows with volume, it's extensive. No, in some circumstances, in circumstances which are important to us, it only grows like the surface. So in one dimension, a surface is always a point, so that's okay. In 2D, it's linear. In 3D, it's L squared, like in a black hole. So if you invert this formula to find the numerical resources you need, you find we are okay in 1D, 2 and 3D are problematic. There are some little ways out in 2D, but that's not our topic today. Now, what I said is, of course, not so much about ground states. We want a time-dependent Green's function, so we have to think about time evolution. And time evolution brings us to some observation, namely it can be shown mathematically that random states in Hilbert space are typically extensively entangled and even maximally entangled. So, and the state which has the number of states which have non-extensive entanglement are actually forming a set of measure zero. But as we know from mathematics, measure zero does not mean empty. So, and what these matrix product states or tensor networks do, they parameterize this low entanglement set efficiently. So for many situations like ground states, which sit in this little corner, this is all fine. But time evolution will leave this cozy corner, and that leads up to an exponential growth of resources, and this is a fundamental limitation of the method. So Hilbert space is huge, and ground states, which we can deal with easily, or low excited states, they're just a tiny little corner in there, and we are getting out in this cold world of the rest of the galaxy. So in fact, one can show, let me focus also just on this equation here. There are some sort of like limitations, which, however, will not so be important for us, is that one can even show that the entanglement can grow up to linearly in time. And given this log exponential relationship, this means that the matrix dimensions you have to use grow exponentially in time. This is the worst case scenario, and one can understand it by quasi-particles entangling system and environment, and they propagate linearly. There has been an entire, hundreds of papers on that, starting with Calabrese and Cardi. This is incredibly well established. Here, the good thing is when we calculate a Green's function, it's only a local perturbation. It turns out, in that case, the matrix dimension growth is only a power law, but this is still bad enough. So, okay, nevertheless, people tried it. And I will not go into the details here, but I think the main thing you have to read on this slide is actually the years of publication. So you see the early work on a single band Hubbard model led to relatively fast results, and good results. In fact, then just going from one band to two band models was so much more difficult that papers only appeared in 2014, 15. I mean, on the one hand, in the Graz group of Hans-Gerd Ewerts, and then in a collaboration I had with Olivier Parcollet, then still in Paris. And we, as I will show for the talk today, we gave up on that. And sort of like there was later work on models with more bands, inventing a very nice new tensor network, the so-called fork tensor network. But whatever you do is, the problem is the reach you get in time is limited by this growth of resources, and that, of course, limits your spectral resolution. This is the key problem of these methods. And so the question is, what can we do about it? And I will present two things. The one is what then leads us to the lithium vanadate, and the other one is then an outlook, what we would like to do next. So the first thing, what we did is, and this was actually in collaboration with Andy. Andy has now disappeared. In 2015, it has been well known that you can put DMFT also onto the imaginary time axis instead of the real-time axis. And this has first been done by Caffarel and Kraut in '94, where they used as impurity solver exact diagonalization. And in fact, the only change in a way is that we replace exact diagonalization as a way of calculating a spectral function for a relatively small system, because ED is of course very limited in the sizes you can reach, by replacing that by matrix product states where the system sizes you can reach are in principle much, much larger, and the approximation you make is extremely small, so you get almost exact results. So this looks a little bit complicated, but this is absolutely standard fare in the DMFT community, just that you pull out ED, replace it by matrix product states. And as I see Antoine, I'm now so tempted to say it. When we had the last PhD celebration for a guy working on that, ChatGPT came up with, explained this entire view graph with one sentence: DMFT is DFT for people who like to suffer more. Okay, so. Yeah, no, that's from ChatGPT, okay? So I removed it from the slide so that it's not being recorded too much for eternity, but that's what it said. I have a few more things which we can discuss in private at some point. I don't know. Maybe it was fed with certain kind of complaints of PhD students before, and then this is what came out of it. But actually, there should not be complaints, because what I want to show you is that it's actually absolutely worth it. I mean, the reason why you want to go to imaginary time is that in imaginary time, which is basically ultimately a projection towards ground states, you don't have this problem of entanglement growth. Of course, you accumulate all sorts of other errors nevertheless, but this fundamental problem of entanglement growth in real time goes away. That's why we did it. So the point is, I want to walk you quickly through 2 or 3 necessary technical improvements, which, however, are only a part of those that A, we have done, and B, that other people have done. I think this is important in the sense that basically we still have a long list of things which one could improve to make the algorithm work better. We are not yet at the end of our options. First of all, one thing which, normally you have the impurity, it's talking star-like to the non-interacting bath sites. So if you map that to a one-dimensional system, you would have something like this with very long-range hoppings. You get this from the numbers here. What NRG, for example, would do, it would transform that to a chain with nearest neighbor hopping by tridiagonalization. There you need it because it gives you a separation of energy scales, which you need there. And if you do matrix product states naively, you would think, short-range hopping, short-range correlations, this is exactly what MPS want, but don't do that. Long-range hopping creates lots of entanglement and so on and so forth. In fact, it turns out no, this is wrong, because there's a very simple physical argument against that mapping, because it brings all the on-site energies, which here are different, because you model an entire band of which has an energy spread. This energy spread is totally hidden here. The electrons just start jumping forth and back, and that creates entanglement, whereas in this picture, all these sites have different on-site energies, which more or less blocks the electrons from hopping too much, and the entanglement growth is in fact much weaker. This was a big step forward, which one had to do. Another one was that even with all these, this is something older, another one which we have to use, even without strong entanglement growth, the amount of errors you accumulate is of course quite a lot after some time, but there is something really funny, which is called linear prediction, where you say, let's think about the values of the Green's function as a time series. And let's try to predict it into the future. And in the following way, that you say your next point in time is a linear combination of the, say, last 20 points or so. This sounds totally weird, but you can train that. Well, I mean, there's no machine learning involved, but you can train that on the data you have to determine these coefficients, and then you can predict into the future. This sounds pretty wild, but the results are really, I think, very, very good. You typically can extend the time domain by a factor of 10 or so. Let me just take this from the transverse Ising model where we have exact results. What DMRG would give you, for example, as a spectral function here for a certain k value is something broad like this. And then if you do this prediction, you get a spectral function which looks like this, and this is right on top of the exact calculation. So this actually allows to calculate extremely precise spectral functions. And the reason behind that is that what this ansatz produces, if you iterate it from one time step to the next, is in fact a superposition of exponential decaying oscillations. So there's an I missing here, sorry about that. And if you think about a Green's function in momentum space, it will have that form here, you all know that. And imagine the self-energy has a single pole, then the Green's function in real time would look like that. And that is what you would get with a sort of like a time series of just one point. So if you have 20 or whatever points looking backward, you can actually get pretty large superpositions, and this seems to be, in practice, excellent for spectral functions. There's more weird things to do, which kept us busy. I just want to walk you why all this took so long and then get you to the results in a second. Of course, we know that Green's functions at large imaginary frequencies, they have to obey a very precise 1 over I omega behavior. It's not proportional. It's exactly 1 over I omega. This reflects the fermionic anticommutator and the definition of a Green's function. So the problem is that large frequencies, they do not correspond really to small times, as we often like to say in a Fourier transform, but they correspond to small time differences. And the usual time evolution methods that people use in matrix product states are time-stepping methods, like delta t forward into time. And that produces sort of like, even if the propagation as such were exact, so if you had an exact Green's function which decays like the red curve, your exact calculation would produce these points. So what do you do? In fact, this actually completely messes up the large frequency behavior of the Green's functions. So there are other methods which get away from time steppers. I just will mention the word Krylov methods. And if you do that, if you do everything properly, and then I get to the results in a second, just want to show you the complications. If you do that properly, and then you compare it to, say, quantum Monte Carlo results, this was for strontium ruthenate, we don't have to go through the details, is you see the curves then all of a sudden sit perfectly on top of each other, even for the large frequencies which previously failed. And what you have here is the green curve is matrix product states. The orange curve is the quantum Monte Carlo, where you see the stochastic noise on top. So all this looks very nice. And the question is now, what can one do with that? And this brings me to the substance which we are hearing a lot about this morning, lithium vanadate, where it turns out, first of all, we could use all these innovations we made. On the other hand, we also needed them. And actually, there are two papers at the moment on the physics, which is the one I will be talking about now, and also the other one by Bakes, Nomura, Arita, who is in the audience in Shinaoka. And actually, in your talk, you showed these two papers next to each other. So I refer to the previous talks. You will see one of the pictures again now in this part of my talk. So if we I think now that we have had the first talk, I think it's of course totally mute to go through all the details of lithium vanadate again. For our purposes, you know, we know that we have the three low-lying T2G orbitals. These T2G orbitals split into two e pi G orbitals and one A1G orbital, as shown in this a picture. And actually what we will simulate is these three orbitals. We will see that also from the band structure, why this is what we should do close to the Fermi surface. Of course, we also heard already about the geometric frustration. We also heard about that the Fermi liquid scale is well below 10 Kelvin. There was a discussion that Antoine already had. We are rather talking about 1 Kelvin or something of that order. And then, of course, why are people interested in lithium vanadate? Again, this needs no repetition. The large mass enhancement below 25K or so. And then, of course, we have had that plot in different colors in the last talk, where we plot as of like transport of charge and heat. And effectively, we have here the heavy fermion curve, and lithium vanadate sits right on top of this curve. And of course, this is why this has been studied so much, because it's heavy fermion physics, or looks like it at least, in a transition metal oxide. But I guess most of you know much more about it than I do. So again, we have these old explanations that, so far, of course, there's no F electrons, so it cannot work, the kind of the standard explanation. So the old adaptation that these bands, the A1G band, which is relatively narrow, takes the role of the d electrons. No, the other way around. And the F, no, okay. That the d electrons are replaced by the A1G electrons, and the F electrons are replaced by the e pi G electrons. But the Kondo-like explanation does not work. I was intrigued to hear from Chandra. Now, this is, of course, something to be thought about, because you said it might be a two-step Kondo effect. But if I understood you correctly, but it's sort of like the old explanations didn't really work. And then one paper which I think inspired us a lot, which was also mentioned already, was the PRL by Arita in 2007, where the idea was that the e pi G bands are essentially bystanders. The A1G band is effectively lightly doped when you take correlations into account, and that it is in effect sort of like Mott physics, which leads to the strong mass renormalization. I think there have been many, many other papers, both in experiment and theory, which I think have been explained already extremely well. From the theory point of view, the common problem is, of course, temperature. I mean, we have sort of like 1 eV is 11,000 Kelvin. This is sort of like a typical bandwidth. We heard already that the physics is happening, say, at 10 Kelvin, give or take, some effects below, some effects, say, between 20, 30 Kelvin, but 10 Kelvin as a rough scale. And in the old days, state of the art was something like 300 Kelvin, which we also saw on one of the plots, on the theory plots in the last talk. So, and what we did is, and perhaps to explain what our stuff like, we looked at that problem. There was a DFT involved for the Hubbard-Kanamori model for the three bands. These were the parameters used. They are very typical parameters groups use for that. And then the original idea was we wanted to see what we can do with a matrix product state-based DMFT solver at finite temperature. For the experts in tensor networks, was done by a purification method. And then something happened which was a bit unexpected. At least I was totally surprised. We managed to push down temperature. Like in quantum Monte Carlo, the high temperatures are relatively easy, and it gets harder when you want to push to low temperatures. We were able to push it to beta equals 4,000, measured in electron volts, or 1 over electron volts, which corresponds to a temperature of 2.9 Kelvin. And that sort of like challenged our quantum Monte Carlo friends. This was mainly Alex Hampel here at Flatiron, to see how low they can go. And Alex ultimately pushed it to 11 Kelvin, and we will look at the results in comparison in a second. And then, because we got to so extremely low temperatures, but still couldn't really reach the clear Fermi liquid regime, we also involved NRG. This was the work of Fabian Kugler for the lowest temperatures where NRG is very good, and for a simplified model. NRG has trouble treating the full Hubbard-Kanamori model. You have to kick out the correlated hopping terms to get some additional symmetry, which makes the solution easier. It turns out, however, interestingly, that didn't make much of a difference. So let me show and be very honest about what we see as problems and as possibilities. First of all, this is a kind of a very theory-oriented talk because it shows the imaginary part of the self-energy, which is numerically a hard quantity to measure. So what you see here is in Matsubara's, the imaginary part of the self-energy at 145 Kelvin with Monte Carlo. Actually, we also have these curves in tensor networks, but then the plot becomes totally crazy. We plot both tensor networks and quantum Monte Carlo at the lowest temperatures quantum Monte Carlo can reach, and then we go further down. There will be another plot where we will also see NRG in a moment. And what you see is, and for this it's probably best to zoom into the very low energy regime that would correspond to 10 MeV, that at around, say, 2 or 3 MeV, something of that sort, so like the imaginary part of the self-energy suddenly starts bending down to become very, very steep. This, of course, you do not see at, say, the higher temperatures because you don't resolve well enough, so you may have a curve like that, and the natural thing would say, well, I continue this somehow to the axis. You only see that at the lowest temperature possible, but you see that sort of like these curves are very nicely in agreement with each other. They trace out the imaginary part of the self-energy very well. And the very important point is QMC is a very established solver, validates the tensor networks very well. But I think one should be honest, this is really pushing calculations to the extreme. What we, for example, found is that when we looked at the baths, which we of course looked at various sizes, more sites in the bath of course makes the calculation more precise, that we observed an odd-even effect in the bath size, which we sort of understand, but still we had to make a choice. Is it either the odd or the even calculation? Both Monte Carlo on the one hand and the knowledge that at the lowest temperature which we should have a Fermi liquid made us understand that which of the two possibilities it actually is. This concerns only the very lowest sort of like Matsubara frequencies, but this is still something where we see we are at the outer edge of what is currently possible. With tensor networks, quantum Monte Carlo rising to the challenge, they really push this crazily enough to beta 1000, which is 11 Kelvin. But then, for example, it's just the warm-up, because the acceptance rate and the statistics became so bad, the warm-up needed 24 hours. Yeah, this is the limit of what is currently possible. But what came out of that? And this is the picture which you have already seen in the previous talk. So the DFT occupation numbers are sort of like shifted around. So the A1G band has an occupation which has a hole density of about 10%, not 2%. So we are further away from the Mott transition than previously thought. But of course, the main result which one gets is here, this thin structure here, which I think is nicer to see here in this plot. This here is that actually our quantum Monte Carlo results, because they have a very nice analytic continuation, is that sort of like at relatively high temperatures here around the Fermi edge, nothing is happening in particular. Then if you go down to 38 Kelvin, you see something is emerging here, and it becomes fully blown, and it's purely in the A1G band. You get a peak, a very narrow peak corresponding to a flat band emerging here right at the Fermi surface, which was also already mentioned in the previous talk. But what you see is you really, to get that fully developed, you need these extremely low temperatures to develop that. At 38 Kelvin, you get an inkling, but sort of like the full structure is around there at these temperatures, which is, of course, changing the physics as was discussed in the previous talk. So the question which was then asked is, of course, where does this come from? And by sort of like varying parameters freely a lot, one could, for example, in particular here, like the Hund's coupling, one can see that the mechanism, this is all figures for 11.6 Kelvin, is that it's the Hund coupling which repopulates the orbitals, and it inhibits the low energy motion by sort of like prioritizing high spin states. This can be seen from histograms where one sees that depending on the number of the total spin you can form, it's always the high spin which you actually form in the end, depending on the number of electrons you have on the impurity. Like say you have 2 electrons, you can either have a spin 0 or spin 1, and the probability of the spin 1 is overwhelmingly large compared to the spin 0. And of course, for 3 electrons, which is a bit rarer, you see the 3½ is much more frequent than the 1/2. So this, of course, the orbitals hopping around in this A1G band, because they are coupling to the ones in the EG bands, this inhibits their motion, yeah, and this is what makes the band ultimately very flat, and this seems to be a robust mechanism under doping and also under the strength of the Hund's coupling. And the important point is the E-pi-G bands are definitely not just bystanders; they are crucial to bring this physics about to get the physics of the lithium vanadate. Okay, there's much more one could say, but I perhaps leave that to the experimentalists. What I would like to say is, in a final plot here, first of all, because we also brought in energy ultimately, which we didn't have in the previous plot, so of the imaginary particle self-energy, so it continues the day. It is now at 0.1 Kelvin. So you see energy is again sort of like an excellent agreement with what tensor networks and quantum Monte Carlo produce at higher temperatures. But what I would like to say is show as a quantity which is experimentally quite intuitive, is the spectral weight at the Fermi edge, which comes from this narrow band which is shooting up at the Fermi edge. So what you have here is what's happening in the E-pi-G bands, nothing in particular. And this is what's happening in the A1G band where this peak is shooting up. And what you see here is we start at 60 Kelvin. This is Monte Carlo results. We do not show the tensor networks because to keep the picture simple. Then Monte Carlo stops here. This is the regime where tensor networks could go beyond quantum Monte Carlo. It directly continues the curve of quantum Monte Carlo. And then this is the lowest we can reach, but this is where NRG takes over, and NRG produces that curve. And this is what NRG then shows at the very lowest temperatures as an inset. But the main point I want to make is that we have now kind of a union of 3 methods which we could employ on a non-trivial problem, which really gives us a continuity from the extremely lowest temperatures, say 0.1 Kelvin, up to wherever we want to go in high temperatures. And given the energy scales that were mentioned, coherence temperature, Fermi liquid temperature, which are extremely low in the lithium vanadate, this is a perfect material to make use of these technical advances. And I think I will not say anything about that because I guess my subsequent speaker, you will talk about that. Okay, so this is then the experiment that comes with it, but this was the experiment of Ricardo Comin, so I would just like to leave it at that. So from my perspective as a a theoretician, okay, this is kind of just summarizing what we have shown, and I think we have conclusively answered the question about the mechanism. But the point, of course, is what can we expect for example, for rare earths, where we would have to take 5 bands or 7 bands, where spin-orbit coupling is very important, and where the temperature scales are extremely low. At the moment, it looks that they should be very likely accessible for matrix product states, probably moving to the trees, which we used in what I will show in the remaining 5 minutes. NRG is limited, unfortunately, to highly symmetric 3-band problems, and quantum Monte Carlo, of course, by the very low temperatures and spin-orbit coupling. So that might be, perhaps for some of you on the experimental side, interesting to use such methods in such cases. On the other hand, what is bugging us is, of course, we are still on the imaginary axis. This was very helpful, but still we would like to go back to the real axis. And this is work underway at the moment. And I would like to report about that paper here, also in a collaboration here with people at Flatiron. On the other hand, sort of like partially the same people had also different ideas on the same issue, and which ideas are best remains to be seen. Probably neither nor, but something completely different. But the point is, we want to go back to the real-time axis, and the way of doing that, it seems at the moment, is by being complicated or complex. And why do we want to do that? Because obviously, say a bandwidth, first of all, there's lots of experimental evidence in the real frequency. Then bandwidth is typically electron volts. Correlation physics is on the milli-eV scale, so we need a resolution of 10 to the minus 3, and this is what currently no real-time method in tensor networks can reach. Of course, imaginary time, that works well. I think this was what the entire rest of the talk was about. But the analytic continuation is difficult and honestly not good at these extremely low frequencies. At least we haven't managed to get something really good out of that. Real-time calculation, I've already said, this is limited by the entanglement growth. So that's what you don't want to do. You don't want to go into the real-time axis, but you can go into the complex plane. And there's, of course, many different paths you can go into the complex plane. For example, you could go at an angle, or you could go up the imaginary and then go into the real axis. What happens in all these cases is that the entanglement, this is what being plotted here, is much, much lower. I mean, we are talking about factors 2 or 3, but if you remember, this translates into exponential differences in resources. So that's a good way of doing it. But then again, we have been doing imaginary time for all the time, like in quantum Monte Carlo. How do we get back to the real axis? This is, of course, the crucial point. Otherwise, no calculation of a Green's function on a path like this one or so is any helpful. And what looks to us at the best way of doing it is going this path, going up the imaginary axis up to some small tau, and then go along the real-time axis. This strongly suppresses entanglement. But the nice thing about it is that there is, if you calculate the spectral function A omega, if you do it at this tau distance to the real axis compared to the true one, there is a very simple analytic relationship where you can sort of like convert the one into the other. So this looks too good to be true. And in fact, it is too good to be true, because there is a numerically nasty problem here. This absolute value of the omega, which pops up in this formula, leads to a kink, because it gives you, so because the A omega, which you are interested in, is typically a smooth function at omega equals 0. I mean, unless you have a special peak there or so, but there's nothing particular as such. Now, in order to get rid of the kink that is in that exponential, this A tau omega has to have a kink, which is then being taken out or compensated by that. No numerics on finite time will give you a curve which looks like that, which has a kink. It will always be softened somehow. And this looked like the killer for the method, but it was a wonderful idea by Olivier, because we were sweating here over that problem and totally desperate, that what you can do is you can calculate that thing for various taus, and then basically, depending on how you choose the taus, you get, of course, different kinks. And by kind of weighing them with positive and negative prefactors, you can set up formulae, I will not go through the details, which eliminate the kink to some power in tau. What we usually do is we eliminate it up to the cubic order, and this looks like an extremely robust choice. So we get rid of the kink, and then all of a sudden we are in business. So what we decided is not to look at a simple problem like the one band, which always works, but we decided to look at a three-band problem, improving over this fork tensor network by moving to another kind of tree geometry, which gives a speed up of a factor of 3 or so, but that's not the main point of the talk here, but that's what one should do, in particular if one goes to, say, rare earths or stuff like this, where this fork network becomes then increasingly difficult. What we did is we looked at three-band models, the Hubbard-Kanamori model, the Tuori-Narat model, where you kick out this double hopping term. We included Hund's coupling. This is not very realistic, but the point is that with the high symmetries in these models, NRG as a benchmark is almost exact, and it's for this Tuori-Narat model, and it's the best current benchmark for the Hubbard-Kanamori model, but only if you sort of like choose the parameters properly. We don't have to do that. That's, of course, the big point. We are free in that. We are not relying on these symmetries. So what one finds is, and we are now looking really at the extremely small frequencies here, 10 to the minus 3, 10 to the minus 2. This is exactly where we want to go to solve the physics. And sort of like the curve you have to look at is the orange one. And the comparison curve is the NRG curve, which here is probably exact, more or less. And what you see is there are deviation at the smallest energies. They are likely due to naive applications of Dyson's equation. There are better ways of evaluating at very low frequencies. And for the Hubbard-Kanamori model, what you get is the orange curve is what we get. The dotted, the dashed, thanks. The dashed curve is what NRG gets. And the interesting thing is they are not on top of each other, unlike here. But what we learned from Fabian Kugler, who is the expert on that, is that he said, this is not exact, we knew that, but he could estimate how this would move if you could push NRG further. And then he says the way it would move is down. Of course, we would not know that it would be totally in agreement, but definitely this is extremely encouraging. And the big point is that we don't need the symmetries that NRG needs. So what we are working on at the moment is to implement that into DMFT as a replacement for these imaginary time calculations to really access also in real frequency the lowest energy scales. But unfortunately there I cannot really show anything yet. So that's for the future. So that's it. Sorry I spoke way too long, but so you read the conclusion on your own, and I'm happy to take questions.
Yeah, thanks, Ulrich, for sharing with us all these exciting developments. I'm personally, as an experimentalist, very grateful that all of this is happening in terms of, calculating spectral functions and interacting systems. But so we have, maybe let's take 2 questions, and then we have a coffee break coming up, so we can continue discussions during the break, and then we'll come back later. Any questions for Ulrich? Yes, Antoine?
Developments, Uli, how do you expect the scaling of the tensor network structure you're using now as a function of the number of orbitals? What are the prospects for doing 5, 7 orbitals?
I think the scaling with the number of orbitals as such will not be bad. It will be more or less linear in the number of orbitals, because this, I mean, naively, I'll come to the but, yeah, because sort of like if you look at this will only be possible on these tree tensor networks, but unlike the fork, which accumulates, it has some. This is now a technical expression. It has one very problematic tensor where a lot of the calculation time is spent. The so-called fat tensor. In a 3-band problem, it's 1. In a 5-band problem, it's 3, and in a 7-band problem, it would be 5 of those guys, and that would then totally dominate calculation time and make it very inefficient. In our case, these trees which we are using are relatively convoluted kind of trees. They do not have the problem. So I would expect, if I just draw the tree, it grows linearly with the number of bands. The problem is, of course, there's the physics. And the physics, of course, say if we go to the 5 or 7 band problems, these will typically be problems where lower energy scales will be particularly important. And that means I have to make the bath sizes much bigger. And this is, I think, where the sort of like where the real question will be. If you gave me a 7-band problem where small energy scales are not terribly important, let's go for it. Yeah, but that's probably not the case. And I mean, we have in the, I think, I mean, if I think about the real-time evolution, which I think is the way to go, just to give the audience an idea, in the imaginary time evolution, say for 3 bands, you have 3 baths, or 6 baths if you split spin up and spin down. They have a length of, say, 12 sides each. Yeah, they are relatively simple. If you do the same thing on the real-time axis, we are talking order 100 and more. Yeah, this is all doable. But if you want to resolve, I mean, you cannot expect to have a vaguely discretized band and get extremely precise information. I mean, somehow the effort in discretizing the band has to grow at the same time. So probably we are looking at 500, 600 sites each, and then of course you have that factor on top, which would be, say, a factor of 2 or 3, I would roughly guess, compared to what we would do now for a 3-band problem on top of the additional number of bands. I would be, on the other hand, relatively optimistic that when it comes to the biggest concern is, of course, the length of the time evolution and how much that costs. We should not be too bad, because if I want to go to 10 to the minus 3, it sets me a time scale which is the same for all of these problems. Yeah. So I would rather see the problem in the discretization of the bands where it would grow. Sorry, that was now a long answer, but it is a very involved problem. Leon, I think, had one.
Yes, Leon, please.
The silvery button. This.
Yeah, I had a couple questions. Beautiful talk about the technical methods and the physics. My questions are about the LIP 204.
Oh my God. Okay.
Sorry. So I guess one is just a quantitative question I was trying to understand. If you could show a couple of plots of the self-energy separated.
Oops, let me. Let me see. I think a good plot for this. This is without. I think that's a good one. Yeah. Mm-hmm.
So the actual values of the imaginary part of self-energy are really big, right? Compared to normally, I would think you have. If I wanted to talk about coherence, I want that to be smaller than the frequency.
Yes. Yes.
Is that right?
Well, I mean, except here in this little corner down here. Yeah, yeah. I mean, this.
Already is way above it, right?
Yeah, yeah. But sort of like for that, it might be good to nevertheless go to the. It's a bit harder to see, but what you have, it's because here, unfortunately, it's not going down all the way to 0. The energy curve, the black one, the one which you see here. I mean, it does the job, but the point is, of course, that sort of like it's really a wild substance. I mean, it stays.
Quite low temperature.
Yeah, yeah. Let's.
I'm sorry, may I ask just a clarification question? Here we're looking at the Matsubara axis self-energy. And for sorry, yes, I should know that. I yell at everybody.
Here we're looking at the Matsubara self-energy. For coherence, we really want to look at something like the imaginary part on the real axis, right? And it's related, but it's not the same. So what do we know about the real axis quantities?
Not much.
Supposing you have on the Matsubara axis, is a fit which seems to be constant plus linear in omega n.
Yeah.
Do we have any dictionary which, there are certain functions in the imaginary axis which we do know what the real axis thing is?
Yeah.
Do we know anything about something like this?
Honestly,
As Leon is saying, you have to reduce by a factor of 100.
yes, yes. No. I mean, both what Andy said is of course totally right. We are looking at sort of like when I make comparisons here to sort of like 10, like at 0.01, which would be sitting here, 10 MeV. Of course, we are confusing real and imaginary to some extent because this is an imaginary axis. Okay, you can measure it in EV, but it's not what we would really think about. So this is an indicator. Of course, you can the mass enhancement. You can of course read off from that curve here, but indeed, I do not know what that would clearly correspond to on the real axis. I mean, perhaps Antoine, who.
Calculate the specific heat.
Sorry.
Given something on the imaginary axis.
Yeah.
You can calculate.
Oh, we did calculate the specific heat. Now you have to remind me. Perhaps Antoine has.
For this factor of somewhere between 10 and 100.
Not.
But you need to lower.
Do you know it by heart, Antoine? Because it was not quite an.
The specific heat is easy. That's
Yeah.
the slope of that guy.
Yes.
Right? So that slope is completely stabilized. It turns out that those calculations they actually give a value of the specific heat which is too large.
It was a factor 2 or so.
And I strongly believe this is a limitation of single-side MFT that doesn't take into account the exchange between sites which quench out the entropy of the system. So that's a separate question. We can discuss it, but it does not
But purely technically, if you can calculate the specific heat, you can go back and express the specific. You can differentiate that to get out the self-energy on the real axis.
I think you are overly optimistic, Chandra.
Can that be done?
No.
No, Chandra.
This sounds like a great conversation.
I think actually.
Sounds like a great conversation for the coffee break.
One more question.
I wanted to say something to Chandra. Let me just say to Chandra, I think I have to look it up, but I think we were big by a factor of 2 or so, something of that sort. And the numerical noise in these curves is, I think, too big to do where Antoine already said no. I think I would not trust anything that would come out of that. Yeah. So, Leon.
Okay, so this is a completely orthogonal question, but just beckoning back to the previous talk, Takagi-san was trying to make a case fairly compelling that some sort of proximity to charge ordering was playing a big role in the humanity. And is there any even hint of this somehow coming out of theoretical calculation?
I don't think we looked at that. Did we look at that at all? I don't think so. We look at it. Yeah.
I don't know if he's now in the room, who has been exactly looking at that.
Yeah.
So I would defer to him to give you an
Yeah.
answer.
In that work, we did not. No.
Okay, I think.
We didn't. We have lots of data hidden in there.
Right, with that, we can maybe close the session. Thanks again, Ulrich.